Okay, let's talk about the elasticity in class problem. You'll notice as I'm going through this, I reformatted my page a little bit so I had more room to write on the screen, but otherwise the questions are all in the same order. So let's look at what's going on here. This whole problem deals with this situation here. We have a demand curve for coffee. So even though this says elasticity of demand for coffee, what we should interpret here is that we have a price quantity graph, and this in fact is the demand curve, and it's a linear demand curve going from up here so at a price of 10 we're saying no coffee is demanded, all the way down to here where we're saying at a price of 1, let's say 180 units of coffee are demanded, and then maybe somewhat unrealistically, if coffee was being given away, there'd only be 200. But the idea is here you get that there's a linear demand curve here. And I mentioned in the lecture that the elasticity along this curve is in fact going to change. And so that's what the first part of this exercise is to actually compute the elasticity of demand at 3 different points on the curve. All right, so the first question here is to find the elasticity using these 2 points along the curve. So we're starting off with a price of 10, the quantity 0, price of 9, the quantity is 20. I've just written the points down here. So how do we go ahead and compute the elasticity? Well, we're just going to use our formula, elasticity, and we're going to use the midpoint formula here. Well, it's percent change in Q over percent change in P. And then we need to use the midpoint formula to come up with these percent change in Q. So the quantity is changing from 0 to 20. So I'm just going to take the difference there, 0 minus 20. And then I'm going to take the average of 0 and 20 as my denominator. So 0 plus 20 divided by 2. And that's the percent change in Q. And now we're going to do the same thing for price. Price's difference is 10 minus 9, so that's our numerator here. Again, I take the difference in prices, and we're going to divide by a base. Under the midpoint method, we use the average of these two, since we can't decide whether it's the end point or the beginning point. So here it's going to be 10 plus 9 divided by 2. And if you go ahead and just punch that in to the math, you get like 200%. So a percent change in quantity is 200%. We get 10.53% for percent change in price, and we get like a number like 19.0. I'm just going to round to 1 decimal place here. I think your sheet might say 2. 1 decimal points, and so we get a number of 19. Highly elastic, right? We're saying that at this point in the curve, we've got a 19 elasticity, so a small change in price is going to cause a 19 times greater change in demand. One thing I should have said here is that the sign over here is actually negative 200%. Because we're subtracting those points. But remember, with the elasticity of demand, remember these are always going to be opposite signs, but by convention we go ahead and take the absolute value of these things, and so that's why we end up with a net factor of 19, because we're just dropping the negative sign. For B and C, rather than go through it all in the video, I'm just going to show them here. So it's the same exact calculation, percent change in Q over P. We're using the midpoint method. We're just using different points here, and we get negative 22.6% over 18.2%. Notice here now when we take that, go ahead and still take the absolute value, we get 1.2. So our elasticity at that first set of points was 19, super elastic. C and D around the middle, kind of near unit elastic, right? Only 1.2. We're saying for every 10% change in price, we'll get a 12% change in quantity, or for every 1% change in price, we get a 1.2% change in quantity. Then down in the lower part of the curve here, we do the same calculation, percent change in Q over percent change in P. Go ahead and go through it all. We get a negative 11.76 over 66.7, 0.2. Now we're actually in a spot that's pretty inelastic. So this is the kind of the numerical demonstration about how even with a linear demand curve, we get different elasticities that emerge. So the next question here is, where is the elastic region on this curve roughly? Well, we saw that this point was pretty highly elastic. So when we think about a linear demand curve, we're going to think about this part up here in the top, upper left, being somewhat as the elastic section of this curve. And then question E is, where's the inelastic region roughly? Well, we saw these points down here created inelastic situations. So we're going to think about this section as the inelastic portion of the demand curve. You could test more points if you wanted to think about this theory a little bit more. And then F, at what point do we think that the curve is unit elastic? Well, certainly it looks like it's, remember, elastic means E greater than 1. Inelastic means E less than 1. So when we use those terms, that's what we meant there. Well, it certainly seems like as we move from something greater than 1 to something less than 1, that somewhere in between here is going to have to be a unit elastic point. And it turns out you'd be right. There is a single point, and we won't exactly prove it here, but it should not surprise you that it actually would be kind of in this midpoint section here. That's exactly where E is going to equal 1. But in this question, I just asked you to kind of guess where you think it would be. But here we see that the quantity demanded is 100, which is halfway across, and the price is halfway across 5, and it turns out that exactly is the tipping point. So maybe that was your intuition also, that it should be kind of halfway across the curve, and that's exactly what happens. In question G, I ask, what's the slope of this demand curve? Well, let's go think about how we think about slope. Well, slope, just think about algebra. Rise over run is what slope is. And so let's think about what this slope of this thing is. So the rise, if we think about the whole curve here, the rise is like $10 of price, and then the run is 20 units of demand. So if we thought about the rise here, we could just think of it as, and it's actually a negative sloping thing, so it's negative 10 over 120. Sorry, negative 10 over 200, which would just be negative 1/20th. If we're thinking about absolute value here, we would say maybe the slope is 1/20th, because what I'm asking you to do is slope the same thing as elasticity? And clearly the answer is no. The slope of a linear demand curve is constant, right? It's this constant number. And elasticity, we saw it's changing across the curve, and it's all different values, and the numbers that we came up with resemble nothing like 1/20th. And so that's the reason we use elasticity, because we wanted to kind of take away the impact of the units. And we talked about too why percentage changes are more important. If a dollar increase, if gasoline increased by $1 a gallon, you might be pretty sensitive. But if the price of a car goes up by $1, you might not care at all. So that's why we think about percentage changes. And so it turns out slope is a driver of the elasticity, but it's not the same thing. So let's just be really clear about that. Slope does not equal elasticity. And I think a lot of people come into this with that assumption or feeling like that's what the case is going to be. And then the last question is, why is the price elasticity of demand changing along this curve? Well, why it's changing has really to do with where the percentage increases are the greatest. And as you might expect, percentage increases are really big near the origin here. Let me say what I mean. Let me say more about what I mean there. For example, if I'm at a price of 1 and I go to a price of 2, I'm doubling my price. So this dollar is a really big deal when I start with really low numbers. And so as I move up the curve further away from the origin, that dollar starts to become less and less of a percentage impact. So here, like a dollar, when I'm at $5 here, a dollar increase is kind of like a 20% increase. Here it's getting more like 10%. So the percentage change gets smaller as I move away from the origin, and the same thing's going to happen on quantity. If I'm going from a quantity of 20 to 40, I'm doubling. So my percent change in quantity is really big when I'm near the origin, and as I move away from the origin, that percentage change gets smaller and smaller. So the dollar or the unit value of the change is the same, but like here, now it's 20% increase, and here it's like a 10% increase. And so if we recall that elasticity is percent change in quantity over percent change in price, sorry, should have been some deltas in there, percent change in price. Well, when we're over in this section, we're up here on the curve. Which coordinate is closer to the origin? Well, it looks like price is pretty far away from the origin, but quantities are really close to the origin. So that means we're going to get huge changes in quantity and small percentage changes in price when we're playing in this area. And that's why it's elastic, because we're getting large changes in quantity for small changes, percentage changes in price. And so because the quantity is the piece that's near the origin here, we get an elastic section of the curve, and then the exact opposite thing happens down here. When we think about points along the demand curve here, which part is closer to the origin? Well, these quantities are pretty far away from the origin. They're almost at the end of the demand curve, but the prices, the area of prices we're playing at is very close to the origin, and so then the exact opposite thing happens. In this case, the big percentage changes are going to occur in the price side of things here. Oops, sorry, changed the color there. Price side of things. And so when big giant changes in price and we have small percentage changes in quantity, that's going to be inelastic. And so that's kind of the motivation about why this is happening. It has to do with which variable is kind of closest to the origin, because when you're closest to the origin, percent changes are the biggest. And again, the elasticity calculation is all about percent changes.